In this video we will design a metamaterial to change the propagation direction and polarization state based on antenna theory. It will be used to investigate the effects of electric conductor array on a flat 2D structure to microwave transmission. In previous experiment we have learned that a polarizer can rotate the polarization axis of microwave. When the transmitter's orientation is vertical while receiver is horizontal, the signal reading is 0. If a polarizer is inserted with some angled polarization axis, the receiver gets some signal. It can be said that the polarizer generates horizontally oriented oscillation of electric field from incoming vertically polarized wave. The propagation direction of the horizontally polarized microwave coming out of the polarizer is the same as the wave coming out of the transmitter. No deflection is detected here. The diagram shows the setup in previous experiment. The transmitter is oriented vertically while the receiver is oriented horizontally. The polarizer is placed between them at an angle. The transmitter generates vertically polarized microwave which then hits the polarizer. The electric charges inside the polarizer's conductor react by moving back and forth according to incoming wave, but their movement is restricted by conductor's orientation. The reactive oscillating electric current in the polarizer generates new microwave which interferes with the original wave from transmitter. The superposition wave is linearly polarized, perpendicular to the conductor in the polarizer. This resulting wave then hits the receiver. Through this diagram we will show how a conductor reacts to electric field. Electric field is depicted by lines coming out of positively charged particle and coming into negatively charged particle. In a dipole where both of them exist nearby, the resulting field is summation of each of them, as shown here. If a free conductor is located around the dipole, it will experience the electric field, which will push charged particles in it according to their charge type, as shown here. This free conductor then becomes a dipole itself, which also generate reactive electric field, in the opposite direction of the first dipole. It will reduce the magnitude of electric field behind the free conductor. If another free conductor is placed behind the first one, it will experience the reduced electric field. So, it will generate lower magnitude of reactive electric field. Here is how a half-wave dipole antenna works as a radio transmitter. Top animation is showing the sinusoidal standing waves of voltage and current on a half-wave dipole driven by an AC voltage at its resonant frequency. Bottom animation breaks down the standing wave into forward wave and its reflection. Here is how a half-wave dipole antenna works as a radio receiver. The antenna consists of two metal rods connected to a receiver. The electric field of the incoming wave pushes the electrons in the rods back and forth, charging the ends alternately positive and negative. Since the length of the antenna is 1/2 the wavelength of the wave, the oscillating field induces standing waves of voltage and current in the rods. The oscillating currents flow down the transmission line and through the receiver. The diagram shows a dipole antenna as a receiver of electromagnetic wave with no load. The incoming electric field is depicted by gray dashed arrow. It generates electric current inside the conductors, depicted by white arrows. The reactive electric fields are depicted by green arrows. Here the horizontal components of reactive electric fields cancel each other. By reversing one of the horizontal conductor, the horizontal reactive electric fields don't cancel each other anymore. Using 1 unit of twisted dipole antenna can only produce weak horizontal reactive electric field. We can amplify the desired signal using constructive interference with another twisted dipole antenna located 1 wavelength away from the first. But this configuration is inefficient, since it leaves a lot of useless empty space. The empty space can be filled by a twisted dipole antenna located half wavelength away from the first. But it must be reversed to create constructive interference, due to reversed polarity in that location. The antenna array can then be completed and repeated in vertical and horizontal direction to cover larger area. Here is the constructed Meander strip antenna array as described before. The conductor used here is enamel-coated copper wire. They are hot glued to a corrugated plastic board. The size of the rectangle is 20 mm width and 7.5 mm height. Now it's time to test polarization twister. The transmitter is polarized vertically while the receiver is polarized horizontally. The receiver is facing right to the polarization twister, but the transmitter sends microwave from an angle, around 45 degrees. We can see that the twister generates adequately high intensity of horizontally polarized microwave to be read by the receiver. When the transmitter is relocated to face straight to the twister, the receiver doesn't get the horizontally polarized signal. This diagram shows the setup in a previous experiment. The distance between vertical conductors in the polarization twister is 20 mm. The transmitter generates microwave with wavelength around 28 mm, so the half wavelength is 14 mm. As explained before, it will make horizontal conductors generate horizontally polarized microwave which interfere constructively, perpendicular to the plane of the polarization twister.